Now it's better, right? Perfect. So glad that you helped me sort that one out. So today we're going to go on a quest. We're going to look out for a crystal ball that will help us to not only identify but also prioritize technical debt. So let's jump right in and see what this is all about. So my starting point is this, Martin Fowler's definition of technical debt. And the idea with technical debt is that just like we can take on a personal financial loan to buy something we want now, we can do the same thing with technical debt. We can make a solution that's a little bit worse, might have some problems, but we can do it quickly so that we can deliver a feature that our users or customers might need. However, the core with both a personal financial loan and technical debt is that technical debt incurs interest payments. And this is something that I have found that the software industry tends to misunderstand and sometimes misuse. And as a consequence, technical debt, the concept, is not as useful or helpful as it could be. And I think I can demonstrate that to you. So now we're going to do a small experiment. What I'm going to do now is that I'm going to present some source code to you here. And your task is to quickly assess the quality of that piece of code. Does that sound okay? Are you prepared? You do look prepared. So here we go. Have a look at this beauty. What do you think about it? Is this good code? How many think this is absolutely fantastic code? Not so many people. Really, just me? Wow. Of course, this is not good code. This is, in fact, horrible code. And we would, of course, never, ever write something like this ourselves, would we? But is it a problem? Is it technical debt? Without more information, we just cannot tell. Because technical debt would mean that we have to pay an interest rate on it, that our software maintenance would be harder. And interest rate is a function of time. So in order to tell if this is a problem that affects us, we will need to have a time dimension into our code. How can we get such a thing? Well, in a minute, I'm going to show you one possible way. But before we go there, I would like to tell you a story about technical debt. So as part of my day job, I work for a company called Ampere, and we do code analysis. So what that means in practice is that I go to different companies, I analyze their code, and I try to come up with a prioritized list of technical debt and some recommendations that you need to fix this and you need to do it this way in order to save time and money. And a couple of years ago, I visited one of our customers, and prior to my arrival, they had used a tool capable of quantifying technical debt. So what they had been doing is that they have taken their tool and thrown it at their 15-year-old code base. And this tool reported that on your 15-year-old code base, you have accumulated 4,000 years of technical debt. 4,000 years of technical debt. Do you know what that means? Let me try to put it into perspective for you. 4,000 years ago, that was here, when Moses parted the Red Sea. So 4,000 years of technical debt. It's a crazy number, and I understand that all that debt wasn't, of course, created during all that time. There had been hundreds of people working on it, but they had taken on a large amount of debt. So how useful would it be to know that the code base you work on has 4,000 years of technical debt? How do you act upon that data? Where do you start to pay off the debt? Well, most of the time, we have no idea. We need much more detailed information. And besides, I actually think it's a mistake to try to quantify technical debt from code alone, because most technical debt isn't even technical. And this is something I've found. I've been working in the software industry for 22 years now, and this is something I've noticed, that in the software industry, we tend to mistake organizational problems for technical issues. So we throw technical solutions at people problems. And I think the main reason that we keep making this mistake is because the organization who actually writes the code, people like us, we're invisible in the software itself. And this is very unfortunate because there is a strong link between technical debt and the organization behind it. And I'm pretty sure that we can never address technical debt. We can never truly improve the quality of our software without taking a holistic view of it. And that holistic view has to include a social, organizational side. So we're going to look into that. And based upon what I've told you so far, I've put together a wish list on the kind of information I think that we need in order to prioritize technical debt and improve our existing code bases. So let me show this list to you. The first thing I would like to know is that given the amount of code we have, in a large industry project, you might have millions of lines of code. Given all that code, where's the code with the highest interest rate? That is the code that becomes more and more expensive to maintain and improve and add new features to. The second thing we would like to know is, what about the software architecture? Does it support the way our system evolves? Do we actually get some help from our software architecture, or are we working against it, which is actually quite common? And third, and finally, and perhaps most important, how does this look from an organizational perspective? Are there any team productivity bottlenecks? Let's say we have 5 different teams working on a particular code base or collaborating. Are there any parts of the code where they need to coordinate their efforts all the time so that they risk running into mistakes? Now, if you worked on a large project or collaborated on a larger project, I hope you agree with me that this kind of information would be really, really useful to make decisions on where should we focus improvements to become a bit more efficient and build better software. What I also want you to note is that if you look at that list, you will see that none of that information is visible in the code itself. So how can we get that data? Where is our crystal ball? It turns out that every single company has a crystal ball. We're just not used to think about it that way. I'm talking about this, our version control data. And version control data, I have this big fascination with version control data. And yeah, I guess we all have our odd hobbies, right? But the reason I'm interested in version control data is because version control data contains exactly the time dimension that we need. With version control, and you see an example from Git here, our version control system knows exactly when we did a change to each piece of the software. And this is something you can use to calculate a lot of interesting statistics, and you're going to see some examples later. What's also interesting with version control data is that it's actually social data. So our version control systems knows exactly which developer that changed which part of the code and when they did it. So based on version control data, we're going to take on technical debt. And let's start by looking at the use case where we can use version control data to prioritize the parts of our code base that has the highest interest rate. This is what it looks like. So what you see here is something I call a hotspot analysis. And I want to walk you through this visualization so that you know what you see. First of all, what you see here is a relatively large Java code base. It's a project called Tomcat, an application server in Java. Is anyone familiar with Tomcat? Some of you. Good. So if you look at that one, you will see a lot of large blue circles, the ones that blink on screen right now. Each one of those circles represents a subsystem, a folder. So this is a hierarchical visualization that follows the folder structure of your code. It's also an interactive visualization, so I can click on it and I can zoom in on any area of detail of interest. And when you do that, you will see that each file with source code is visualized as a circle. Now, you will see that those circles have different size. That's because size is used to represent something called code complexity. That is, how hard is this code for a human to understand? So is anyone familiar with any metrics for code complexity? How can we measure that? Does anyone know? If you look in the industry and you look at the research papers, you will see that we have a bunch of different ways of measuring code complexity. So we might have things like cyclomatic complexity, cognitive complexity, We can count the nesting depth in the different logical decisions, stuff like that. And what all of those have in common is that they're equally bad. We just don't have a good way of predicting that. It's not a solved problem. So what I tend to do is to use the simplest thing that can possibly work. And it turns out that lines of code is a pretty good approximation of the actual code complexity, how hard it will be for me as a human to understand it. Besides, this is not the interesting dimension. The interesting dimension is this. Do we actually work with that part of the software or not? And this is data that we can pull out of our version control system. So we can look at the behavior of the developers and see, all right, this particular file has been modified 200 times over the past year, for example. So we sum that up and use color to represent the change frequency. And when we combine these two dimensions, we're able to identify complicated code that we have to work with often. And that's our hotspots. So you can view code complexity as a measure of the amount of technical depth you have there, and you can view the change frequency as a proxy for interest rate on any technical depth. Now, let's return to Tomcat and have a look at the hotspots. So you see that the hotspots identify a relatively small part of the code base. And this is a small part of the code base where we need to focus and ensure that the code is good enough. Because if we have any technical depth in those hotspots, it's going to be very expensive because those hotspots are changed all the time, which means that every change is more expensive to the organization than it has to be. However, more often than not, the worst code I tend to find is in the hotspots. And that makes hotspots excellent refactoring targets. And there's a fascinating reason why hotspots work so well as refactoring targets. So let me ask you, has anyone read something from the author George Orwell? Is anyone familiar? Like maybe half of you? How many have read the Animal Farm? Cool. So the first time I read it, I thought, like, this is spot on. George Orwell, he really understands software. Because you might remember that in Animal Farm, George Orwell wrote that all code is equal, but some code is more equal than others. And I thought, yeah, that's exactly how it is, right? And I'm pretty sure what George Orwell was referring to was my next slide here, this one. So please have a look at this. What you see here are 3 different graphs that represents 3 different systems. And you see that those systems, one is Roslyn or C# Visual Basic compiler, you have the Erlang programming language, and the Ruby on Rails platform. And those 3 code bases, they are developed by different people. They target different domains. They have a different lifetime span, implement in different languages. Everything is different. And yet, if you look at those graphs, do you see any similarities? Yes, that's right. They all show exactly the same distribution. They show a power law pattern, a Pareto distribution. Let me show you why this is important. The data you see here takes each file in our code base, and that's what you see on the x-axis, and sorts the files on the change frequency. How often do we as developers work with that file? And the change frequency, the number of commits, is what you see on the y-axis. Now, this power law pattern is something I've found in every single code base that I've analyzed. And I think I've analyzed like maybe 300 code bases over the past years. And this is important because it gives us a tool to prioritize technical depth and code improvements. Because what this means is that most of our code is going to be in the long tail. So this is code that's rarely, if ever, touched. Our hotspots are going to identify the head of the curve, the parts of the code where we work the most. So that's where we want to focus improvements. And using a hotspot analysis, you can identify refactoring targets that are as small as maybe 2–3% of a total code base based on data from how the organization has actually worked with the code. So hotspots are a very, very good starting point. But sometimes they're not enough. And I want to show you an example where hotspots don't work that well. So let me show you a code base that I think a lot of you are familiar with as users. So how many run Windows on your laptop? Half of you. So you have this piece of software on your laptop. This is the .NET Core Runtime from Microsoft. And when I did this hotspot analysis, like maybe a year ago, most of the hotspots, you see, they tend to cluster here. You see them in here in a package called JIT. So this is the just-in-time compilation support in .NET Core. Now, what you also see is that there seems to be another hotspot, kind of like a satellite here. This is something called ge.cpp. This is the .NET garbage collector. And ge.cpp, it might look quite innocent on this visualization, but that's only due to the scale of .NET Core. This is a big, big code base. In fact, what you see here is close to 4 million lines of code. And ge.cpp is a big file. How big? I really don't know. Let's look it up on GitHub, shall we? So it turns out it's a pretty good capacity test of GitHub, because this file is actually too large to visualize with syntax highlighting. So we need to look at the raw file. And when we do that, we see that ge.cpp is a single file of C++. There are 37,000 lines of code in that. 37,000 lines of code. Isn't that a lot? So, how many of you have been programming C++? Ah, plenty. Plenty. I also used to do C++. I was a C++ developer for 10 years. I know what some of you are thinking. Those are 10 years I never get back. And that's true. That's definitely true. But what it also means is that I can definitely sympathize with the maintainers of this part of the code. 37,000 lines of code. That's the stuff nightmares are made out of. And besides, how useful would it be for Microsoft to know that ge.cpp is a hotspot? How do you act on that data? You know, it's just like the 4,000 years of technical debt. It's so much code, it's simply not actionable, right? So we need much more detailed information. So what I do when I come across those large hotspots is that I use something called an X-Ray technique. So what I do here is that I take that large hotspot and then I parse it into the separate functions and methods. And then I look at the Git log, where do each commit hit? And then I sum it up. And that gives me hotspots on a method level. Let's see how that looks on ge.cpp. Here we go. So what you see here are the function level hotspots in ge.cpp. And we see that the number one hotspot is a function called grow brick card tables. And we see that that function consists of 332 lines of code. So one could argue that 300 lines of code in a single function, it's a little bit more than what fits into the human brain. But still, I would claim that we are now on a level where we can act upon this information, because 300 lines of code is much, much less than 37,000 lines of code, which was the size of a total hotspot, right? And it's definitely less than 4 million lines of code, which was the size of a total code base. So we are now on a level where we can do a specific code improvement or specific refactoring based on how we have worked with the code so far, which means we can expect a return on that investment. All right. I want to stay with ge.cpp for a while, because first time I did that analysis, I started to think, how can you get to a single file with 37,000 lines of C++? How does that happen? I mean, no one wakes up in the morning and says, today I'm going to write a file with 37,000 lines of code, right? That's usually not what happens. And I get some inspiration for that from one of my favorite books. This is a recommendation to you. This is a book called The Challenger Launch Decision by Diane Vaughan. Has anyone read that book? No. So put it on your wish list. It's a really, really good book. And in that book, Diane Vaughan talks about the Challenger accident, the space shuttle accident. So can anyone remember what happened to Challenger? Some of you. So I'm going to cover it for the rest of you here. So the space shuttle Challenger. This is Challenger on its final launch back in the 1980s. And if you look closely at that one, you see this is the actual space shuttle. This here is the main tank with rocket fuel. And this is something called a solid rocket booster that's used to lift the rocket out of the Earth's atmosphere. Now, if you look closely at that picture, you see a puff of gray smoke here. That's not a good thing. It's not supposed to be there. So what actually happened with Challenger was that those solid rocket booster joints, those are large, large rockets. I think they're like 45 meters or something like that. So they are delivered in different segments that are then assembled before launch. And it turned out that one of those segments, one of those joints, failed to seal, so hot rocket gases were able to escape and impacted the structure of the whole space shuttle. So once it got into the air, it simply disintegrated. And the end result was not only a loss of a space shuttle, but a tragic and completely unnecessary loss of human lives. Now, what Diane Vaughan does in her book is that she uses the space shuttle Challenger accident to coin her theory called Normalization of Deviance. Because it turned out, already in the early 70s, when the first design tests were made of those solid rocket booster joints, those tests revealed that those solid rocket booster joints, their actual performance deviates from their predicted performance. That's not a good thing. You're building a spaceship here, right? So what do you do in that situation? If you're NASA, the answer is pretty simple. You form a committee. And they did. And they discussed the problem, and they decided to pass it off as an acceptable risk. Years later, in the early 1980s, during the first in-flight tests, again, the actual performance of those solid rocket booster joints deviated from a predicted performance. And again, it was discussed and passed off as an acceptable risk. And it continued like that for years, until actually on the very eve of the launch, there were some concerns raised by some engineers due to the unusually cold temperatures in Florida at that time. And again, it was discussed and passed off as an acceptable risk. And we all know how that went. So this is what Diane Vaughan calls the normalization of deviance, that each time we accept a deviation, we get a new point of reference. The deviations become our new normal. And Diane Vaughan, what's fascinating is that she's not a software developer. She's a sociologist. But the reason I tell you this is because this has nothing at all to do with spaceships and everything to do with people like us, humans, people who write code. And we have plenty of normalization of deviance within software development too. So let's give you an example. Let's say that one of you go to work for a company. And on your first day there, you become responsible for a particular module. That module might be a large, large mess, 5,000 lines of code, which is a lot. And at first, you're probably not that happy with it, but spend enough time with that code, and it starts to become familiar. You start to find your way around. And besides, what difference would a few extra 100 lines of code do, right? So soon you have 6,000 lines of code, then you have 7,000, and so on, all the way. So we need to find a way to identify when we are falling into this normalization of deviance trap. So one technique I've been using for this is something I call complexity trends. So here's what I do. When I find a large hotspot, I go to its version control history and I pull out each historic revision of that code. And then I measure two things. I measure the code complexity by using any one of those metrics that count the number of branches and stuff like that. And I use the lines of code. And I plot a trend like this over time. And if you do that, you will find that every piece of code has a story to tell. And the complexity trends help you read that story. So the example you see here is from a piece of code I worked on myself. And you can pretty much see it here that at first we seem to have done some refactoring. So we managed to reduce the complexity, which is a great thing. But we most likely failed to address the root cause. So pretty soon the complexity keeps creeping in again. And then in early 2017, there was a steep increase in complexity. And this is something I always use as a warning sign, that it's time to take a step back and reflect upon what we really do. Is this really the best way to evolve that code? Complexity trends help us ask the right questions. The normalization of deviance is one of the reasons that whistleblowers are so important in organizations. And I have found that those complexity trends, they're excellent whistleblowers for code. So to sum up this first part of the presentation, using hotspots, you can identify the technical debt with the highest interest rates. And that's where you want to focus improvements to make sure you get a real effect on them and that you're not just wasting your time improving things in that long tail. And the reason Hotspots works is because all code is indeed not equal. Now, I want to talk about one more thing. I want to show how the techniques can scale up and let us reason about whole software architectures. And first thing I do when I want to analyze a software architecture is that I need to specify what are my architectural boundaries? What kind of architectural building elements do I have? So what I do is I typically introduce something I call logical components. So what I typically do is I take a bunch of files and say, all right, all of these, they belong to one particular component. So when I go to the Git history, I aggregate all the data for any of those files into a logical component, in this case called DRM shared. Or I might say that everything under a particular folder is represented as a logical component. So I raise the level of analysis to more abstract concepts. And you can do hotspots that way. You can find architectural hotspots, which is interesting in a large system. But one technique in particular that I would like to show you is something called change coupling. So has anyone heard about change coupling before? No one? You have heard about it. For the rest of you, I have something new. That's good. So you might be familiar with coupling in general. This is something software developers typically talk about. You have a piece of code here. You use some code over here. They're coupled. They have a dependency on each other, right? And this is something you can see in the code. But change coupling is different because change coupling is invisible in the code itself. It's something you can only uncover by looking into the version control data and the evolution of the code. So here's how it works. Let's say we have 3 different services, maybe web services, right? And the first time we make a change to that system, we have to modify the fuel injector and diagnostics module together. The next time, we modify some other service. But the third time, we're back to modifying the fuel injector and diagnostics module together again. Now, if this is a trend that continues, we know that there has to be some kind of relationship between the fuel injector and diagnostics module because they keep changing together over time. This is a technique we can use to evaluate how well does our architecture supports the way our system evolves with new features. So I want to show you an example from 2 different architectural styles. Does anyone recognize this architectural pattern? Yes, like half of you maybe. What is it called? MVC, yeah, a true classic, right? Model View Controller. And you will find other variations, model view presenter, model view view model, and so on. And the technique I'm showing you now applies to all of those. So in my day job, when I come to organizations and I'm supposed to analyze their code, one of the first questions I ask them is that, what kind of architectural style do you use? And 9 times out of 10, they say, yeah, we have a layered architecture, we have a model view controller. And then you look at the code, and that's never ever what it looks like. Isn't that fascinating? Because if you talk to people in the industry that's been around for a couple of years, they all know that this is not enough. We need more layers. We might need something like this. Because we all know we need some kind of repository layer, right, that encapsulates the interaction with all the data objects. And I think the main reason that we need a repository is, you know, actually, I don't know. I've been thinking about that for years. I have no idea why we need it. So, you know what? We're just going to call it a best practice. So we don't need to motivate it. And of course, this is not enough, because we also know in the industry that you need a data abstraction layer, because you don't want to access your SQL directly. And again, I think the main reason we introduce stuff like a data abstraction layer is because our solutions might be too simple without them. Might be too easy to reason about. So we need more of a challenge. And of course, we know that this is not enough. We also need a business layer. It's really important. So to end up with an architecture that has like 10, 11 different layers, it's not uncommon. What I do now to reason about the cost of that architecture is that I consider each one of those layers as a logical component, and then I measure the change coupling. And that lets me see how the daily work looks with respect to software architecture. This is what the change patterns look like in a layered architecture. In fact, I have the data from my research shows that somewhere between 30 to 70% of all commits, all changes we do, ripple through the entire software stack. And if you look deeper at it, you will see that most of those changes are trivial. Let's say we want to add a checkbox on or off to our application. So we had something visible in the UI, and now we have to make a predictable change across the whole stack. This looks rather expensive, don't it? Right? And I think the main reason here that we end up with architecture like this is that, do you know what the main motivation is behind a layered architecture? There's one term I tend to hear over and over again, and that is a separation of concerns. Ever heard that one? Yeah, some of you, right? And with the layered architecture, we do get the separation of concerns. But we separate on technical responsibilities. Each one of those layers represents a technical responsibility. And that means a layered architecture is optimized for things like switching out a layer for a different implementation. And a classic example is that you need to change the database, right? So you just change the database layer. And I spent 2 decades in the software industry, and that has actually happened twice, which means that like once in a decade, this is a good architecture. The remainder of the time, what actually happens is that we do a trade-off. We optimize for a very, very rare scenario at the expense of something that happens every single day, which is to expand it with new features. So I think that these shortcomings of layers is one of the reasons that microservices have become so incredibly popular over the last years. So how many are familiar with microservices? How many have heard about it before? It's like 60% maybe? Cool. So the idea with microservices is that instead of building one large system, you build several small systems and let them communicate with each other. And the fascinating thing with the microservice architecture is that each one of those services might be really, really small. It might be like 1,000 lines of code, 2,000 lines of code, so it's pretty easy to understand. However, the emerging system behavior is often anything but simple, because most of the complexity in a microservice architecture is in the interactions between them. How do they talk and communicate to each other? And now, what you can do using these techniques I'm showing you today is that you can do a change coupling analysis on microservice level. So you consider each microservice as a logical component, and then you measure the change coupling between them. And what you want to look out for in this case is anything that's surprising. So what would be surprising in a microservice architecture? Well, anything that's expensive. For example, stuff like this. We have multiple services that continue to change together over time like this. So you modify one service, you have a predictable modification to 4 other services. Why is that so bad thing? It's a bad thing because the moment you start to couple the lifetime of different services to each other, you lose most of the promised advantages of microservices. You will no longer be able to develop a small system in isolation because it will always depend on 4 others. You will never be able to deploy that system independently because it will always require changes to 4 other systems as well. So strong coupling is like the cardinal sin in a microservice architecture. And if you use change coupling and you do those analyses early and regularly, this can help you avoid what I call the microservices shotgun surgery pattern. And that's basically when you want to tweak a single business capability, you want to add a new feature or something like that, and you end up modifying a bunch of different services together. And in practice, I've seen several reasons why that happens. One of the most common reasons is that you have multiple services and they share code that itself isn't stable from an evolutionary perspective. Another reason this might happen is because API design is really, really hard. And some services, they typically communicate via something like a REST API or a service bus. And some services may just suffer from suboptimal APIs. So they expose implementation details, and now all the other services that depend on that service start to depend upon implementation details, which ties the lifetime of those services together. Finally, I've seen that from an organizational perspective, this problem seems to be more common when the same team is responsible for multiple services, because now it becomes so easy to start to assume that, oh, the information I need over here So I just send a query, and now you're tying those two together. So using a change coupling analysis, you can evaluate your architecture and find out how well does it actually support the way the system evolves. Now, the last thing I want to talk about now is the social side of code. The stuff we don't see in the source code. So how many of you have developed software as a team together with one or more peers? So that's like almost everyone, right? A few that haven't. So in the software industry, almost all code these days is written by teams. There are very few applications that are developed by a single individual. And there's a reason for this, of course. We take on larger and larger problems. Our systems become more and more complicated. So it's too much for a single individual. So we need to form a team in order to be able to make that work. And you have probably heard about all the benefits of teamwork, all those wonderful things that happen when humans get together. What we rarely talk about is the other side, the cost of teamwork. And that's what I want to spend time on right now. Because the cost of teamwork, any teamwork, is pretty well known within the field of social psychology. So this is a model of teamwork called process loss that the social psychologists have borrowed from the field of mechanics. So the idea is that just like a machine cannot operate at 100% efficiency all the time due to things like friction and heat loss, neither can a team. And here's how it works. Let's say we have a bunch of individuals. Together, they have a potential productivity. But that's never, ever what you get out of a team. The actual productivity is always going to be smaller. And part of the potential is simply lost. How does that happen? Well, it depends on the domain you work in, but within software, the tasks we work on tend to be interdependent. They depend upon each other. So that means that a lot of the process loss in software is due to things like coordination overhead and communication overhead. And the bad news are we can never entirely eliminate process loss. What we can do is to try to minimize it. And one common reason for process loss in software is something called the diffusion of responsibility. So the diffusion of responsibility is, again, another concept from social psychology. And what this means is that if you're unfortunate enough to witness an accident or an emergency, what you will see is that the larger any group of bystanders, the more people that are present, the less likely that any individual will offer help. This is actually quite scary. So that means if you should have some kind of emergency situation, it's better to just have one or two people witnessing that. It increases the chance that you will get help than if you have a large group with like 100 people. This is kind of scary. And this is the diffusion of responsibility is a complex phenomenon. But one of the explanations is that in a larger group, we'd no longer feel a personal responsibility. We kind of just assume that someone else will help instead. And it's the same thing with code quality issues and technical debt in software. In a large group, it's not my problem. Someone else wrote that code, right? We don't have that sense of personal responsibility. And I think that's very unfortunate because I'm pretty sure that good code is code where everyone involved has that sense of personal responsibility, that I'm responsible for this code, for the quality of it and its future. I don't think there's really any way around it. So if we have an important principle like that, like the diffusion of responsibility, how can we measure it? How can we measure the people side of code? It's easy. Remember, we are in version control wonderland. So we have all that social information on which individual that wrote which code. What I do now is I take the individuals and I aggregate them into teams. So 2 people on the same team, I aggregate their contributions. And that lets me calculate a map like this. It's the same kind of visualization style that we saw earlier for the hotspots, but now the color carries a different meaning. The color shows an overlap in the code contributions between members of different teams. So the more red something is, the more different teams have worked on that part of the code, which helps us identify those parts of the system that become coordination and communication bottlenecks. And you see some examples here. So one of the things I would do, this information is never easy to act upon, but if you're would be like the architect behind a larger software system. You would use this data. First of all, you would start to investigate it from a technical perspective. Because a very common reason that code becomes a coordination bottleneck for multiple teams, that multiple teams have to change the same part of the code all the time, is because that code has too many responsibilities. It does way too many things. So to take that code and split it into smaller and more cohesive parts will actually help you improve the organizational side of software as well, because now you create natural boundaries for your teams. Another thing that's very, very, very common is that you have some shared code that's used by multiple different services. And that shared code might lack an ownership. If everyone owns it, no one owns it. So you might find that you have to introduce a new team into the organization to take on that shared responsibility. Now, using this data, we can do even more. We can start to measure things like Conway's law. Has anyone heard about Conway's law? Some of you, a few of you. So let me quickly do a quick recap here. So Conway's law is basically a principle that says that the way you're organized as a company, your different teams, departments, will be reflected in the systems you create. So your software architecture will look like your organizational structure. And this is not necessarily a bad thing, because it's actually something that helps you facilitate the communication between different departments and teams. Now, using version control data, we can start to measure Conway's law. So you can get a completely different view of software development here. So you see an example here. This is an architecture, same visualization style as before, but now the colors signals the contributions of the different teams. So we can identify the parts of the code where each team do most of their work. And we see that from the perspective of Conway's law, this looks absolutely beautiful, right? You see there are clear boundaries between each team. So you have a very clear mapping between what the organization looks like and the architecture. So your teams carry a meaning from an architectural perspective. That's really, really good. So I have to tell you something. This is all data that you have seen in this presentation so far is from real-world code bases that I've worked on, except this one. I had to make it up because I'm yet to find an organization that's that well aligned with the code. So let's look at a more realistic case. This is actually real data from a system, from an organization I worked with a couple of years ago. Now, what happened here was that this organization were going to do something called feature teams. So right now in the software industry, this is a huge trend. If you look back a couple of years, most organizations tend to be component-based, which means that you and your team, you were responsible for this component. And the problem with that is that you tend to get pretty long lead times. So in order to implement a feature, you need to have that team make that change, that team have to make that change, and so on. So it becomes expensive. So people shift to feature teams, where a single team can work across the whole stack. They have all the expertise that they need. And this organization did that. They introduced 12 different feature teams, and they did iterations. They did some variation of Scrum. So in the first day on that iteration, they assigned each team a bunch of tasks like this, basically a round robin. And this map shows the contributions of the different teams over a single month. Can anyone spot any patterns in that? Neither can I. Because what you see here is a complete communication disaster. This was incredibly expensive. And the main problem here that you see is that virtually you have 12 different teams working the same parts of the code, but for different reasons, since they work on different features. Not only does that put you at risk for things like conflicts in the code, you get merge conflicts, you get incompatible changes. What it also does is that it opens up this window of opportunity for the nastiest bugs you can ever have, which is things like unexpected feature interactions. So in this case, they actually, once they saw this data, they actually had to roll back and realign their component teams, because this got even more expensive. So whatever you do, please align your architecture and your organization. Your code is going to thank you for it. So the last thing I want to show you is that maybe you would like to try this out on your own code bases, on your own projects that you work on, and find your own hotspots. So this is still a young field, which means that the tooling options are relatively limited. So it's fascinating to know that you can get really, really far with just a simple Git client. So here's an example how you can identify the coordination needs between different individuals on a specific component. So you can get far with the Git client. If you want to do more advanced analysis, you need some type of application logic and scripting on top of Git. And when I wrote my first book, Your Code is a Crime Scene, like 5 years ago, there weren't any tools available that could do all the stuff I wanted to do, so I had to write my own tools. So I put them together in a tool suite called CodeMat that I've open sourced. It's available on my GitHub page. It's completely free, as in both speech and beer. I don't earn anything from it. So have a look at that. That might be a good starting point if you want to find your own hotspots. If you work on open source software, or you have student projects that are open source and are on GitHub, what I work on these days is something called CodeScene. So CodeScene is a service that's entirely free for open source, and it provides an automated way of running all these analyses I've shown you today and some more, including the visualizations of it. So if you enjoy these techniques, please consider to have a look at it and support it. Finally, I'd like to point out that there are some interesting tools in the academic space as well. So one of my personal favorites that I just want to mention is something called the Evolutionary, which is pretty good at the change coupling on a file level. So it might be worth to have a look at that one too. Now, I'm almost done now, and I hope you enjoyed this journey through the field of evolving code, where we finally found our crystal ball. Because ultimately, it's all about writing better software. And writing large-scale software systems, like we do all the time in the software industry, is a hard problem. And the hardest problem to solve is not necessarily code quality. We know how to write good code. The hardest problem is all the existing code that is already there. How do we prioritize our limited time and money so that we get a real return on investment when we do some improvements? And I think that problem will never be easy. So I think we need all the support we can get. And I hope that this presentation has inspired you to investigate the field in more depth. And I put together a number of references for you in case you want to read more. I have a new book on the topic called Software Design X-Rays. Came out in 2018. I blog about the topic regularly at empir.com, where I have a bunch of different case studies and show different applications of these analyses. And now, before I leave some time for questions, I would like to take this opportunity and say thanks a lot to every one of you for showing up today, and may the code be with you. Thanks.
Thank you very much. Does anyone have a question?
First of all, thank you for the lecture. You have showed the graph with a line of code versus the complexity of the code. So my question is, how did you measure the complexity of the code, and why do you think it was probably unnecessary, and how did you measure? How did you know it was unnecessary? Thank you.
So it depends on what you're after. When it comes to hotspots, I'm really just interested in, is it likely that the code is overly complex? And there you can basically use any metric that you want. So that's where I tend to use just lines of code to get a quick assessment, and then I might dig deeper. But when it comes to a trend, the reason I plot the 2 lines is, first of all, lines of code is easy metric. The code complexity, I tend to use things like McCabe's cyclomatic complexity. You basically just count the number of possible paths for your function, number of if statements, number of loops, and sum it up. And the reason cyclomatic complexity is not a good metric, but it gives you, it works as a rule of thumb. And the rule of thumb I typically use is that everything that is above 10 in cyclomatic complexity is likely to be a problem, because it ties into the limitations we have of our working memory, how much information we can hold in our head at once. And the reason I plot those 2 lines is because most of the time you will find that they follow each other. They're almost parallel. But sometimes you will see that the lines of code increase, but the complexity increases at a more rapid rate. And that, when that happens, carries some signal, because what it means is that not only does your code grows, it grows in a particular way. And it tends to grow through more and more complex constructs. So it's not just that you get more code, it's typically that the code that is already there becomes more and more complicated. So I hope that answers your question. Cool, thanks.
So first of all, the question may seem a little bit silly. How is your job called? Like the name specifically? And how come that you changed your job from software developer to this? Because personally, I don't like to look at other people code. And I think it's really hard to get, to know what they mean for it. And that you do it for the living. And yeah, that's it.
Yeah. So interesting. So I'm still a software developer. I write code almost every single day. And my company is called Ampere. So it's a startup, started in 2015, a very small company, bootstrapped, no venture capital and stuff like that. And we do two things. We do tools in this area. So if you look at ampere.com, we have some commercial tooling capable of doing a lot of other analysis, including in-depth code analysis. And since we're a bootstrap company, in order to finance that, I decided to do the analysis as a service. Because there are a lot of companies, they don't really have time to buy a tool and learn it. They want someone to come in and kind of help them. And I have a lot of expertise in working with legacy code. And the reason I continue to do that is because I find it really fascinating. I'm learning so much. Because every single year, I get to see maybe 20, 30 different organizations. So I get a lot of influences from there. And I think in particular, if you're developing a product, I think one of the most important things you can do, I think it's even more important than any technical decision that you make, that is to make sure that you yourself are a user of your product. Because it makes it so much easier to build a good product. So when I do the analysis, I use our own tools to do that. And when I find that, all right, this is pretty hard to do, then I realized that, all right, we lack a feature in our tool that could do this for me. So that's the main reason I continue to do it. Hope that answers your question. Thanks.
Do we have more questions? No? Okay, so,
So you shown us that the hotspots happen when there are many changes in a few files, yeah? And this doesn't matter the language or the framework or the project. In every project and language, it is that most changes are made in only a few files. And do you have any theory why this happens?
Yeah, so it's kind of fascinating, first of all, that those power laws, they are everywhere in software. It's not only about change files. If you look into things like, I have a background, I have a degree in psychology, which is one of my biggest interests. So I'm really interested in the people side of code. And we look into things like contributors on a code base. You will see that you have the same power law there. Most of the code is written by relatively few people. So I think that might be just nature. I think the reason that hotspots continue to be hotspots is because there are multiple things. First of all, I think the software industry is pretty bad at fixing existing technical debt. It's just not visible. And most developers, when you do a hotspot analysis and you show them that, look, these are your top 10 files that are likely to be problematic, they tell, yeah, I know that. And I think that's basically just, a hindsight bias. Because with software development, it's so complicated. We do different kinds of work every single day. We might work on different features, different parts of the product. And the things that happen over time is something that I think the human brain is not particularly well suited to pick that up. So we don't see the long-term trends. And I think that hotspots are usually problematic from the start. You get something wrong in the design. And then you build on that, so it becomes worse and worse and worse. And once it gets to a certain level, you will see that you have to go into those hotspots all the time to do bug fixes. And over time, they will become like behavioral magnets that everything that's relevant to your system is centered inside those hotspots. So you have to change them all the time. So I think that's the main reason why that happens. So by the way, I'll be hanging around for the rest of the afternoon. So if you want to discuss more about this, I'll be around, be happy to discuss it.
Okay, so once again, thank you very much for your lecture.
Thanks.